Okay, so in this video we're going to explain the fact that cone complexes have no homology. So what do we mean here by a cone complex? It's like this. So a cone complex is a complex that simplicial complex K that has a cone point. Cone point is like this. It's a vertex of the complex with the property that for every simplex sigma, if we take sigma and add in the p as well, then that's still a simplex. So a key point about such complexes is that they're contractible. To see this, I mean, you've got some point x that lies in geometric realization of k. Well, it will lie in the realization of some simplex sigma, and then you can have this bigger simplex, probably bigger simplex, sigma union p, and so p is in that, and so the straight line from x to p is contained within this simplex sigma union p, and so in particular it's contained within the complex k. So so we can just move along that straight line. That gives us a contraction of the whole complex to the cone point P. But what we're going to prove in this video is that the homology of a complex like that is very simple. That the zeroth group, h0k, is just a copy of the integer z, and all the other homology groups hij, for I different from 0, those homology groups are all just the zero group. As a basic example of that, of course, k could just be a single simplex. In that case, any vertex counts as a cone point, and so we find that the homology of a single simplex is just this single copy of z. So to prove this, we're going to use a chain homotopy, as we've discussed in the previous video. So we're going to define this map S from CRK to CR plus 1k. And it works like this. We've got a generator of CRK is given by some simplex V0 up to VR, and to apply S to that we just put in a P at the beginning. So notice that P could in principle already appear in this simplex V0 up to VR that we first had, and then you'd have two P's on the right hand side. And according to our standard rules for these kind of chain complexes, when you've got the repeated P, that means that the thing just counts as 0. So what we're doing here is, if we've got a simplex that doesn't contain p, then we're just inserting p, and if it does contain p, then we send it to 0. And then there's some issue about plus or minus signs. We've got the usual sign convention for how we list the vertices, and so that's going to come in some places later. But yeah, so let's consider what happens if we just have a generator x for C3k. So that's going to be given by a list of 4 vertices, v0, v1, v2, v3, and we'll use the usual kind of abbreviated notation, just call that 0, 1, 2, 3. So for, to do with chain homotopies, we have to think about dsx and sdx. Okay, so let's do dsx first. So sx is just p, then 0, 1, 2, 3. Then we apply d to that. So we get a bunch of these 5 terms here. The first term where we omit the p and just get 0, 1, 2, 3, which is the original simplex x. And then the other ones, they all still have the p, but one of the other letters has been omitted. So here we're omitting the 0, that comes with the sign -1. Omitting the 1, that comes with a +1. Omitting the 2 with a -1. Omitting the 3 with a +1. But then we also need to consider s of dx. So remember, here was x here, and so dx is this thing here that we get. The first term we omit the 0, the second term we omit the 1, and here omitting the 2, here omitting the 3, with alternating signs as usual. And then we apply s to that, which just means we stuff in a p at the beginning. Okay, and we notice that what we've got here, these 4 terms, they're just exactly the same as these 4 terms here, except the signs are opposite, right? I mean, why are the signs opposite? I mean, you look at this term here. I mean, here this occurs as the kind of as the 0th term in this on this side, so it comes with a sign -1 to the power 0. But it occurs as the number 1 term here, so it occurs here with the sign -1 to the 1. So here you've got a minus, here you've got a plus, and it works the same for all the rest of them. They occur opposite signs in this expression and this expression. So when we consider ds plus s dx, which is what we're supposed to do for a chain homotopy, then we find that basically everything here cancels, except that this term is left uncancelled. So ds plus s dx is just this 0, 1, 2, 3, which is the original x. Or if you like, you can call that the identity applied to x. So what we're basically saying is that we take ds plus sd, then that's equal to the identity. Now, there's going to be a little bit of a glitch which happens at r equals 0. We're going to have to consider that case separately, but But for all the cases where r is bigger than 0, they all work the same way as this C3 case that we just discussed. Everything cancels out and we just get ds plus st as the identity. So what does that tell us in homology? If you consider a homology class here, square bracket z, an element of the homology group HRK, so z is a cycle, with dz being 0. Okay. So then if we look at z, well, by what we said here, ds plus st is the identity, so z is the same as dsz plus sdz. But dz was 0, so this second term, sdz, that's just 0, and we just get that z is the same as dsz. But in particular, it's d of something. In other words, it's in the boundary group brk. But remember, this square bracket z, that just means the coset z plus brk. And if z is actually in brk, then that counts as the 0 coset. So what we've seen is that any element of this hrk is just the 0 element. Okay, so this group hrk is 0 when r is strictly positive. Now let's just look at the C0 case. That's just going to be a tiny bit different. Okay, so dx is 0 because dx is now going to lie in C minus 1 of x, and that's just the 0 group by definition. So sdx is 0. And so this ds plus sdx, that's just a d of sx, which is d of p comma v. And here, just remember the definition of d, we omit the p, leaving bracket v, or we omit the v, leaving bracket p, so you've got bracket v minus bracket p. So that's what happens on C0k. So now let's look at a cycle z in Z0k. Okay, but Z0k, remember, that's just the same as C0k. Z0 is the kernel of the map from C0 to C minus 1, but C minus 1 is 0, so that kernel is the whole group C0. So that means that z can be expressed as some of these vertices a multiplied with by some integer coefficients na. So let's let n be the sum of all these coefficients. Okay, so basically you've got a bunch of points with multiplicities, and we're just taking n to be the total multiplicity. Okay, so remember dz was 0, so sdz is 0, but dsz, you've got the sum of all these na times the things that we get from this formula here, which is bracket a minus bracket p. So these first things, the sigma na pointy bracket a, that's just your original z back. But then here you've got the sigma a pointy bracket p, right? And then because the pointy bracket p is always the same, what you're just sort of counting up, adding up all the na's. So here you get z minus n times p. Okay. So because you've got this d of something is z minus n times p, that follows that in as cosets, the coset of z is the same as the coset of n times p, or bracket z is n times the coset of bracket p. And that works for any element in Z0, so we find that all you've got in your H0 is just the multiples of this p.